presentation is on development activity between Earth Engine, Python data. And so really what we're talking about is large amount of environmental geospatial data tools for. What we're looking at here is a marvelous view of Earth from 35,000 kilometers in space, captured by those 6 other satellites. And what we can see here is the Western Hemisphere. It's rotating towards the sun and away from it. Water moving through the atmosphere in the form of clouds. We can see hurricanes spinning out in the Atlantic. Earth is just wildly dynamic, right? We have shorelines, forestation, tree growth, lake and reservoir levels rising and falling with influence of agriculture, meandering rivers, Amazon rainforest, urban expansion in Las Vegas that are seasonal, like vegetation and snow cover, things north and south. So all of those events, things that happen on scale of year or multiple years, but there's also events that happen on scale of days and hours, like wildfires that burn through forests, grasslands, sometimes communities. Other events like hurricanes or events. And so there's lots of satellites and terrestrial sensors that are continuously collecting data. Data are being fed through models, systems for consumption, scientists, NGOs, private companies, agencies, for them to monitor. And they're generating of data, the scale of trillions of observations, bytes, data sets. And so, it sort of ends up being this big data problem, data too little time, and how do you handle it? And of course, lots of computers in the cloud. And so Google's system for handling large spatial data sets is Google Earth Engine. And it's a distributed computing platform, large scale environmental geospatial data. And it has 3 main components. First, starts out with this massive data catalog where Earth Engine data team is continuously updating and ingesting new data sets, streaming data. It's a mirrored copy of publicly available, often as raw satellite imagery, derived product. And when we ingest them, it's optimized to work with Google's system. And that data is co-located with compute servers, and then you access this data and the compute. And so what this kind of looks like is in the client, write some. So for instance, region on Earth you're interested in, time series, and maybe there are 100,000. Write a function, Earth Engine, this thing, and maybe in the end, mean statistic. And so you express this computation, Earth Engine data classes, for things like an image and image collection, all of those data classes, function, methods, describing that you write instructions, those instructions across the web, Google's servers, and the instructions are interpreted, and the job is divided up among workers, essentially. And then some result could be sent back to you, back to the client, some small amount, or maybe the result is really large and exported. And so I like to think of it as sort of a data distillery, data wood chipper, some kind of processing that takes a lot of raw material and reduces it down to a meaningful bit of information. And so what this looks like, processing geospatial data, is that you filter a whole bunch of data to a time, region, and you do some kind of reduction on it. the mean, or take a bunch of images and predictive model over it to generate raw data and reducing it down. And then at the end, maybe some more refined analysis table chart. And so Earth Engine can do all of this, but it's particularly good at these first two, filtering lots and lots of data and reducing. And it inherently its work among many nodes. And so there's one of the convenience about Earth Engine is that there's no setup involved to configure a cluster. Inherently knows how to divide up big, huge jobs, give you back a. And another nice advantage is that geospatial data, it's representing data that belongs here, but data are often arrays, which are dimension. And so graphic data is often warped field into 2D field. And there's hundreds of different projections, all different ones. Different satellites have different scales for their pixels. So grids just often never, and in order to make them line up, you have to do get them all projection. But with Earth Engine, it works on a kind of pull basis. Whatever you want the analysis to happen in projection and the scale, very final thing of your script basically says, I want all of this to happen in this projection, this scale. And when those instructions get to the server, it sees that. And before it does anything, it reprojects all of the data. You don't have to do it. Just tell it that's the projection. But maybe it's not so great with analysis. This is where Python data format libraries really shine. And so for sort of historically, Python with Earth Engine, to describe it as a little bit janky, that you could do really well, but the analysis part of it, the result, you're with maybe tips that you get back or a blob that you have to parse out. And so we've been working on ways to activity between Earth Engine, Python. So over the last year, we've added data connectors, data formats, pandas, GeoPandas, SciPy. And one of the more exciting things that has happened in the last couple of years is GEMAP came out, which made it type and interact with data notebook environment. And this opened up the possibility and the interest for working with Python more. Quickly visualize your data. All this data is tiled, so you could zoom in and out of the Earth rapidly. It's dynamic. All image tiles can be clicked on, values, instead of just looking at a static plot lib. Interact with the data. It really helps with prototyping. Build a lot of interest around maybe we can start to do more of a Python. And it's become a really popular project. People are using it. It's often first place that people are being interested in spatial data analysis. Sensing map. And Google has now adopted it and are including it as the recommended tool to use as kind of like an IDE if you're working with Earth Engine data. The recommended do it now. Front end team helping to support and is okay. And so we've gotten to this point where we're about to want to do an analysis, data to do the analysis. So there's two primary places where we get data: our public data catalog and a community project. You can also just bring your own data to Earth Engine, stored in Google Cloud.
So one of the interesting things about that makes Earth Engine uniquely different from a lot of other places. When it first came out about 2011, and by 2013, there was already the Landsat collection on Earth Engine. It's browser-based remote sensing because the idea is not only are you independent of the load or the burden of actually copying these data sets on computers, it also allows for the compute to be run on Google servers rather than your, that even if you have the data that are sitting on buckets, a lot of the times you are running into situations where you need an instance, whether it's on Binder, whether it's on Colab, whether not it, and sometimes those machines are large enough, there aren't a lot of memory allocation, storage issues. So there are some benefits and there are some differences between running them in the batteries included mode, which is JavaScript mode, the analysis ready mode. I want people to be aware of those. The data piece is really, really interesting because the catalog, the main catalog, right? Click on this one. The main catalog is on master catalog. It's about 100 petabytes and it's getting about 1 petabyte of data. The data comes from different sources like Sentinel, from Landsat, Modis, and publicly available. There are also providers of data sets who will frequently update their own data sets. So you can have other publishers of their own data sets. For example, WRI data is provided by WRI. There is some from the community catalog that's actually part of this catalog itself, created by. So a lot of data sets already exist in the main catalog. In about 4 years ago, there was a data set request that came from an individual contributor or individual user of Google Earth Engine asking about Facebook generated high resolution settlement population data set at 30 meter. Turns out that was one of those data sets that wasn't on Google Earth. There's hundreds and thousands of those data sets. Don't necessarily know all the data sets useful to all research. 4 years ago, I started a project where I started with that one data request and I said, what if we took the research products that a lot of labs are producing and a lot of people are actually generating as part of their research work and integrate that and build that around a catalog that's maintained. Somehow the data set request comes from users. I don't have to basically be an expert in every single field. My background is in hydrology, hydrologist, but if someone else wants to give data on agriculture, give data on forestry, is hey, the data is in here, it's in this Zenodo repository, it's in this Dryad or Figshare repository. We actually get to it and make it just as simple as so this was the birth of the community catalog. What I'm going to do is I'm going to really quickly walk through both of those catalogs, just to give you all like what it actually looks like. This is the main catalog. If you come into the main catalog, you can go and see they have been grouped into some of these categories if you wanted to. What I really like doing. And you can actually browse through all of these data sets that are here. You can look at the different information about a data set. So for example, if I wanted to look at forest age, for example, if I click on that data set, it'll give me a little bit of description and information. There's usually also Explore with Earth Engine code. So if I wanted to just click on open in code editor, it'll just open that code directly in code editor and should be able to run. The data set is active. How easy it is for basically just say, I want to go from this data set, read about it, know what the band. The community catalog was born around the same idea, was because it wanted to support, hey, there are a lot of good products that are using, but research data, just like research papers, are often locked behind walls. But the fact that not everywhere a place in the world has this width and download speed. Not everyone is carrying around an 8 terabyte hard drive in their that they can. So the idea was to basically same level of data sets. So if, for example, if I wanted to go and pull the hydrology data set here, the idea was similar. I'm pulling in all of these data sets weekly. I'm working towards making it happen. And if someone wanted to look at, for example, the global river obstruction data set or something like that, they can basically click on a sample code again. What this should do is open up also in Earth Engine, able to run. It allows people to then directly access. And one last thing that I wanted to that this is open for people to contribute to. So if people wanted to add their own data sets, they can go to this website and actually give this back.
Okay, so now we have covered the data. So next, I'm quickly go through some of the ways that you can get the data out of Google Sensing and interact with the Python side. So we're going to talk about both vector data and raster data and how you can get the data out very easily just with one line of code. So here, this is just some simple user examples. They are unlimited examples. You can. So here, the simple example, if I ask you which US state has the highest mean elevation, for those of you by looking at the map, can you guess? Give me the answer. Was top one highest elevation, average elevation? Colorado. What's the top three? Okay. What's the lowest three? Right. You can guess. You can try it out. But this is something that we can use because DM can be many gigabytes, right? You can do random computation, so we can basically utilize the massive computing power of Google Engine. You can get the result and then do some plotting. So here, just one line of code, you can run zonal statistics using Gmail, and then once you get the result of feature collection, just one line EE to PDF, then you can turn it into a data frame. Then you can just sorting, so you can easily figure out which one is the highest, which one is the lowest, whatever you want. It can be DM, it can be temperature, it can be vegetation, it can be wind speed, it can be anything. Okay, so just an example. And then you can just one line of code, you can utilize the SciPy or Python packages, matplotlib or plotly or anything. Gmail also has one line of code. Just create a bar chart using the table we get out of Google Engine. You can see clearly. Another example, right, where I can be working, for example, assume you're working at USDA. You want to figure out which US state has the largest agricultural area. Can you tell me here? Just looking at the map, or you might already be familiar. So you can, we have the land cover data NLCD, so it's a huge data set, many gigabytes. We can just use Google Sensing to the computing power. Again, one line of code, zonal statistics using Gmail, and then you can get the data out, the land cover statistics, and you can turn it into a data frame. And again, you can quickly, easily see, for example, Iowa, Kansas, right? So those are the top areas. And again, it can be any categorical data. It doesn't have to be land cover. So if you're dealing with large data set, global scale, anything, one line of code, the statistics, get done, and then plotting. You can create bar chart, you can create pie chart. Again, everything is one line of code in Google, in GNet. So it's so easy to use. You can do it easily. So that's for data frame, but you can also turn into geo data frame. So if someone want to create some maps from the result, again, you can run the same analysis, and then you can just E to GTF. Then you get the geometry. Then you can use GeoPandas or any Python packages plotting, for example. The same thing, right? Getting the result from DN statistics, and I can run this one so you can see the different categories of elevation here, average for all the states in the US. Similarly, you can do that for agriculture. Again, you can just use GTF and get the statistics out easily. So that's for traditional pandas and geopandas, but we also have tasks. If you need some large data set getting out, so in this map showing here, this is the global power plant database with almost 30,000 points. You can just one line of code, use the DAS EE package, and then just read the package, and then you can get all the data out in seconds. And it's very fast, very powerful, and then you can run analysis, for example, create some plotting, or use any task or functions, and then you can change the function, you can do analysis, plotting. So these are some examples you can create easily by utilizing the data set on Google Engine, and you can run analysis or you can get the data out pretty. So that's for vector data set. Google Engine is most suited for raster data sets. It's over 100 petabytes of sector data, anything you can think of. So there are different ways you can get the data out. If you only want a small data set, you can use the Gmap function e to numpy. So you can pass any images, and you can get a small piece of image outside of Google Engine. Then you can use, for example, Matplotlib or any. This is for small data set, but for large one, we also have the XE package that allows you to get the data to extra rate. So in that way, you can large scale analysis and can get the data out. So this is a simple example. For example, dealing with the EIA5 hourly data set, right? So you can For example, I choose month July 2023. So you can use the Google Engine to do all the data processing, or you can get the raw data out if you want to, and then you can turn that into an X-ray, just one line of code. And after that, you can run analysis, X-ray, whatever functionality available X-ray. For example, this is July 2023, the mean temperature by aggregating the 744 stamps, right? Because it's hourly, 24-hour, and so you can get it in seconds, and you can run the analysis. The reason I chose this example because NASA reported July 2023 was the hottest month on record. So we have the data. You can verify if you're someone very skeptical about like what they are putting out there. You can run the analysis, a couple lines of code. You can do the same thing. You can verify the results. So this makes things really scalable and also reproducible. And similarly, right, if you really someone into X-ray, you can use it to create this kind of plots. Monthly, for example, I take out the whole year of data 2023, and then I can run the aggregation to get you the temperature for each month, and then you can see the dynamics of it. Of course, everything this can be done also in Google Sending. We're just showing you a way that if you are really someone that want to are already familiar with X-ray, but you're not quite familiar with the syntax of Google Sending, you can get the data out. So it's very, very easy to do. By the way, so all the examples I show you in the upper right corner, I forgot to mention there's a Google Colab link. You can open, you can run it by yourself. Everything is reproducible, so you're going to see get the same examples. And if you're someone that not familiar with X-ray, you're from Geospatial, you're only familiar with GeoTIFF. Okay, I just added this function this morning. It's X-ray master, so you can turn it into a GeoTIFF or cloud optimized GeoTIFF, whatever you want, and then you can open using Desktop.js. So basically, you can get whatever data you want, and then read it as X-ray. You can large amount of data, and then you can turn it to GeoTIFF. You download it to your computer, save it to a computer. Of course, you can also turn it into a NextDF, right? So just the X-ray to NextDF, so you can get whatever data format that you are familiar with. It's very, very powerful. So basically, we have these all connectors that can help you to connect between the massive computing power Google Engine, and also you can use it to finish up your data analysis or your plotting or whatever way that you are comfortable with using the Python ecosystem. So we cover both the vector and raster data. And recently, I also built another package called HyperCodes that allows you to visualize hyperspectral data. So if someone wants to deal with a lot of X-ray and then you have a lot of bands, you can also do something like this. The reason for that is this GIS we usually can only visualize RGB, right? But the time series data or the hyperspectral data can have hundreds of bands, thousands of bands. You don't want to load all of them into the desktop GIS, all the data layer, but this one can help you just sliding through. And this built onto PyVista, so help you visualize data. You can just sliding through, select whatever band you want, or the time period you want, and then just visualize that. So a better way of visualizing geospatial data. And similarly, you can also do interactive thresholding. So if you think about here, it looks cool, but this gives you a way for you to easily see, for example, the temperature in 2023 in every location at what month the temperature surpass certain threshold, right? You can traditionally you can open all the layer in GIS and then trying to go through each layer, but this one gives you a 3D structure, so you can easily see in this location, this couple months past the temperature. So it can be temperature, it can be wind speed, it can be soil moisture, it can be anything. So just give example. So these are some of the ways that you can interact, getting the data from Google Sending, computing, and then visualize using whatever Python package there are for me. And lastly, there's a demo. Okay, maybe I can quickly show you here. Again, this is the notebook in here, and if you want, you can click the link. You can scan the QR code, and you open on Google Colab. You have the Google Sending account, then you can just run through it. Everything is with, so you can try out yourself. Of course, you can also run it on your local computer. Everything is interactive. You can train things. You can do computations, customize area. So the nice thing about Google Sending is that you don't have to worry about the area. You don't have to worry about the time because most data set is global scale and then lot of time periods. So we can focus more on science, spend less time on do the data management. So really powerful. So you can try it out. And if you have any questions, we're happy to. And here's the slide. If you want
We'll open it up. It's who's hosting does the
Most of the community catalog data sets are being ingested for the some users host their own data sets and they make it so then the catalog points to the data set rather than so there's about 325 terabytes of community hosted data sets community catalog. Majority of those, like large chunks of those, be held by the community own repository. About 80 to 90 terabytes of those hosted by the space is given to me by Google Earth Engine. As far as if you're asking complicated in terms of egress cost, that's a whole different conversation. If you're asking complicated in terms of just copying it over, it's not very difficult because you just have command, you can chain a command that is AWS copy and you copy it over to a GCS bucket. And then from GCS bucket, you can ingest it. So Earth Engine usually gives you about 250 gigabytes of storage space that comes allocated to the project. But if you really have cloud storage and if you have amount of money or funding available to host that data yourself, you can keep terabytes of data on Google Cloud Storage. I think it's just standard storage cost. It's not that difficult. It's probably a couple of lines. Is it okay to go the other way from Google to Amazon? Okay, feel free.
if you get the data out to accelerate, then it's outside Google Engine, not in the cloud anymore. You will need to utilize those compute power available in your machine. So the recommended way is do everything possible in Google Engine, all the computing, and there's something that's not really possible, then you get a small subset data out and then you continue. And then you can use whatever way that you're familiar. So yeah, once you get the data out, it's not optimized. Just like you're watching a movie on Netflix, it's streaming, it's fast, but if you're trying to download the last high resolution and then get to computer, then you need to have some hardware to actually create it. That's why we usually recommend don't try to get the whole raw data set, terabytes data out. Even if you get it out, you cannot really compute. You need the large computing power. So try to do things in cloud and then small things that you fine tune or whatever using your local computing power or your Python environment. And everything that you, for example, X-ray, or the any local geotip, you can still visualize the data using GMap. GMap can visualize both data from Google Sensing or any local data set, vector data set, geotip, just egg vector or egg raster. Call.
use or plan.
Yeah, certainly it's something we're thinking about because we know for large vector data set, if you have Pyro and other data sets, easy visualizing Longbow or other packages. That's something I will experiment it first using DeepMap and then I'll pull it.
Okay.
Thank you very much.
I have one more